Good morning to all of you. In previous session, we have seen representations of discrete time signals. Okay. So we have seen four different representations, that is functional representation, graphical representation, tabular representation, and sequence representation. So any one of these four representations can be used to represent any discrete time signal. So today we'll be looking at some elementary discrete time signals which can be used to perform some complex operations such as convolution, correlation, Fourier transform, discrete Fourier transform, fast Fourier transform, Z transform. Okay, so these are very important discrete time signal, basic discrete time signal, which can be used to perform some complex operations. So the first elementary discrete time signal, okay, so today we will be discussing these elementary discrete time signals. Which are also called as basic discrete time signals. Okay, so first one is the unit sample signal. This unit sample is also called as unit impulse signal. So these elementary discrete time signals are used to perform, or these can be utilized in some of the complex operations such as convolution, correlation. Okay, so first one is the unit sample or unit impulse signal or sequence. This signal is denoted as del of n, and functionally it can be represented as del of n is equals to 1 for n is equals to 0 and 0 otherwise. So what does it mean? So the signal del of n has value 1 only for n is equals to 0. That means only at origin. Okay. So graphically this signal can be represented as, so here I can draw its graphical representation. On x-axis I can represent discrete time small n, and on y-axis I can represent the signal value, that is del of n. Okay, so time is 0, 1, 2, 3, 4 and so on. Similarly -1, -2, -3, -4 and so on. So this del of n has value 1 at n is equals to 0. So at n is equals to 0 it has value 1. Okay, so there is only one non-zero value, that is at n is equals to 0, that is at origin, and at remaining value, for remaining values of n, that is for n is equals to 1 it is 0, n is equals to 2 it is 0, as well as 3, 4 and so on. For all the remaining values of n, it may be positive or it may be negative, the value of del of n is 0. Okay, so this is called as what? Unit sample or unit impulse sequence or signal. This is the first elementary discrete time signal. The second one is the unit step signal. Third one is the unit ramp signal, and fourth one is exponential signal. So now let's look at what is unit step signal and how it is represented. So in case of unit step sequence or unit step signal. This unit step signal is denoted by u of n, small u of n, and functionally it can be represented as small u of n is equals to 1 for n greater than or equals to 0 and 0 for n less than 0. That means for positive values of n, the value of u of n is 1, and for negative values of n, u of n is 0. So graphically I can represent this u of n, that is unit step signal, as, again, on x-axis I can take discrete time, that is small n. On y-axis I can take u of n, time as 0, 1, 2, 3, 4, 5, and so on. Similarly, -1, -2, -3, -4, -5, and so on. So at n is equals to 0, u of n is 1. Similarly, for n is equals to 1, again it is 1. For n is equals to 2, it is again 1. For n is equals to 3, again it is 1. For n greater than or equals to 0, everywhere it is 1. For 5, again it is 1, and so on. And for negative values of n, for n is equals to -1, it is 0. For n is equals to -2, again 0, -3, 0, -4, 0, -5, 0. Okay, so how this unit step sequence or signal can be represented graphically as well as in functional form. The third one is unit ramp signal or unit ramp sequence. So it is denoted as small u r of n, small u in suffix r of n. So in functional form, this unit ramp signal can be represented as ur of n is equals to n for n greater than or equals to 0 and 0 otherwise. So this is functional representation of unit ramp signal. Graphically, it can be represented as, again, I can draw the graph of this unit ramp signal. All these are the predefined signal, that is unit sample, which is also called as unit impulse signal, then unit step, and third one is the unit ramp. All these are the predefined signal which can be utilized to perform complex operation in digital signal processing. So graphically, this unit ramp signal can be represented on x-axis. I can represent discrete time small n. On y-axis I can represent the signal values, that is ur of n. Then the time is 0, 1, 2, 3, 4, and so on. Similarly, -1, -2, -3, -4, and so on. So when value of n is equals to 0, the ur of n will be 0, right? Because I am substituting the value of n here, so n will be 0. So for n is equals to 0, ur of n is 0. For n is equals to 1, the value of ur of n will be, that is ur of 1 will be 1. Okay, so gradually this signal value will be increasing with the increase in the value of n. So for n is equals to 2, again the value of ur of 2 is 2, then ur of 3 will be 3, right? Ur of 4 will be 4, and so on. So signal will be increasing for positive values of n as the value of n increases, and for negative values of n the signal value is 0. So that means for -1 it is 0, for -2 it is 0, for -3 it is 0, for -4 it is 0, and so on. So likewise, these three elementary discrete time signal can be described. Okay, so first one is your unit step signal, which is denoted as unit sample signal or unit impulse signal, which is denoted as del of n. Second one is the unit step signal, which is denoted as u of n. Third one is the unit ramp signal, which is denoted as ur of n. Now fourth one is the exponential signal. Fourth one is exponential signal. So this signal can be denoted as a function of n. X of n is equals to a to the power n. So where this small a can be any real number, right? So this signal, that is exponential signal, will exist for all values of n, right? So it is defined for all small n. It may be positive value or it may be a negative value. The signal value will exist for all values of n, and it is defined as x of n is equals to a to the power n. So just for example, if I want to, so this is nothing but the functional representation of the exponential signal. Okay, so this is the functional representation of exponential signal. Now if I want to represent this exponential signal in graphical form, so the value of exponential signal will depend on, as you can observe here, the signal value depend on the value of a as well as value of n. Okay, so just for example, again I can represent on x-axis the discrete time small n, on y-axis I can represent signal value, that is a to the power n. This is nothing but your x of n. Okay, so again time is varying as 0, 1, 2, 3, 4, 5 and so on. Similarly, -1, -2, -3, -4, -5 and so on. So just for example, if I am considering the value of a, right, value of a is greater than 0 but less than 1, right? So how this signal will look like in graphical form? As I am considering the value of a is greater than 0 and it is less than 1, that means it can be 0.1, it can be 0.2, it can be 0.25, it can be 0.45, it can be 0.67. Okay, so likewise any value can be taken as the value of a which is greater than 0 but less than 1, right? So in this case, when I am substituting value of n is equals to 0 here, so the value of signal will be a to the power 0, that means it will be obviously 1, right? So just for example, if I am considering the value of a is equals to 0.2, 0.2, right? So then a to the, that is 0.2 to the power 0 will be 1, 0.2 to the power 1 will be 0.2, so this is your a then, right? Then there will be a square, so a square will be 0.04, so which will be less than basically 0.2. Again a cube will be less than your a square, then a to the power 4 will be less than a cube, a to the power 5 will be less than a to the power 4, right? So likewise the signal will be decreasing, right? It is decaying. And when I am substituting value of n is equals to -1, so in this case it will be simply look like this. Okay, so how it will be look like? So when I am substituting value of n is equals to minus 1. So then it will be obviously greater than, so it is what? It is basically A inverse, or you can say 1 by A. Okay, so in our case it will be 1 upon 0 0.2. So what is the value of 1 upon 0 0.2? So it will be greater than 1, right? Similarly, when I am substituting n is equals to minus 2, so it will be 1 upon a square. So this value will be greater than 1 upon a. Similarly, when I am substituting it as minus 3, right, then minus 4, so these are nothing but the values, so I can indicate a to the power minus 4 or 1 upon a to the power 4, right? So then something, so this will be 1 upon a to the power 5 or 1 a to the minus 5, and so on. Okay, so likewise the signal value will be decreasing, okay, as I have taken the value of a which is greater than 0 and less than 1. Okay, so that is first graphical representation of this exponential signal for this condition. Okay, so I can taken this condition as where the value of a is greater than 0 and less than 1. Okay, so if I'm considering another condition, right, if I'm considering second condition where I am taking the value of a greater than 1. So if I'm taking value of a greater than 1, that means it can be 1.2, it can be 1.5, it can be 4, it can be 6, it can be 100, it can be 1000, or it can be anything, okay, which is greater than 1. So again, if I want to plot this exponential signal in graphical form, again on x-axis I can indicate time, on y-axis I can represent the value of signal x of n. Okay, so again I can take time here 0, 1, 2, 3 and so on. Similarly minus 1, minus 2, minus 3 and so on. So in this case, just for example, if I'm taking value of a is equals to 3, right? So again for n is equals to 0, the value of signal will be 1, right? Because a to the power 0 will be 1, a to the power 1 will be a, but now this value will be greater than 1. Okay, this value will be greater than 1 because we have taken a greater than 1. Then obviously the a square, as if I'm taking a is equals to 3, then at n is equals to 1 the value of signal will be 3, at n is equals to 2 it will be 3 square, that is 9, at n is 3 it will be 3 cube, that will be 27. Okay, so that means your a square will be greater than a and a cube will be greater than a square, okay, and so on. So in this case the signal is increasing, okay, and if you are taking negative values of n, so obviously for minus 1 the value of signal will be less than 1, so this will be your a inverse, right? Then it can be a to the power minus 2, this can be a to the power minus 3 and so on. So on left hand side signal is decreasing, on the right hand side signal is increasing. So this is how the exponential signal will be represented for this second condition where we have taken a greater than 1. Okay, in first case we have taken the value of a between 0 and 1, in second case we have taken the value of a greater than 1. Let's look at the third condition. Okay, if I am taking value of a is equals to 1, okay, if I am taking value of a is equals to 1, so irrespective of value of n, everywhere the signal value will be 1 for all values of n if I am taking a is equals to 1, right? Now take a look at another condition where I am taking the value of a as is greater than minus 1 but less than 0. Okay, So what does it means? So it means the value of A can be minus 0.2, minus 0.4, minus 0.87, minus 0.97, right? Minus 0.99, minus 0.465. Likewise, any value can be there within this range, can be assigned to the value of A. If I want to plot this signal, so how it can be represented? Okay, so instead of I will try to insert one more slide here, okay, because this graph cannot be accommodated. Okay, so what we are trying to do, we are trying to obtain this exponential sequence for another condition where value of a is minus 1 less than a less than 0. Okay, so just for example, if I want to draw the graphical representation of this signal, okay, again on x-axis time will be represented here the signal value x of n, which is a to the power n, and the value of a between this range. That means a can be minus 0.2, it can be, or it can be any one of these value, right? Minus 0.2, minus 0.876, right? Minus 0.58, any value which is within this range. Okay, so if I'm taking this value, so again when I'm taking the values of discrete time small n and trying to identify the value of a to the power n, so how these values will vary now. So for n is equals to 0, again the value of signal will be 1, right, irrespective of any value of a. Just for example, if I'm considering it as minus 0.4, okay, as value of a is minus 0.4, so minus 0.4 raised to power 0 will be 1, right? When I'm taking it as minus 0.4 raised to power 1, so it will be minus 0.4, so it will be negative value, right? But it is less than 1 basically. When I'm considering it as, when I'm taking it as, so this is nothing but your a, okay, that is minus 0.4. When I'm taking a square, so it will be minus 0.4 whole square, so it will be 0.16, so this will be less than this a, sorry, this one value, right? So this is your a square. Then again a cube will be minus 0.4 raised to the power 3, so again it will be a negative value, right? But in this way this can be represented and so on. Okay, similarly for minus 1, so it will be minus 0.4 raised to the power minus 1, right? So this will be a negative value, okay, but this negative value will be like this, okay. So this is your not a inverse. Then if I'm taking minus 0.4 raised to the power 2, that is minus 2, minus 0.4 raised to the power 2, sorry, minus 2, because here n is equals to minus 2, so this value will be, again I can take it as 1 upon 0.4 square, right? So it will be simply, it will be 1 upon 0.16, right? So this value will be, again this will be greater than 1, okay, 1 upon 0.16. If you take this value, in numerator and evaluate it, so it will be greater than 1. So this is your a to the power minus 2. Again, for minus 3, this value will be negative, so this will be a to the power minus 3. So like this, again this signal is decreasing, okay, but samples are present, or samples are having positive or negative values, right? So this is how this exponential signal is represented when you are taking the value of a within this range, that is -1 less than a less than 0. Now let's look at another condition. This will be our last condition, right? There we are considering the value of a less than -1. Less than -1 means, so a can be -2, -3, or it may be -2.25, -5.56, any value, right? So I can consider any value of a which is less than -1. So if I'm considering a is equals to -3, just for example. So again, n x of n will be there, right? So it will be a to the power n, right? So again, time value 0, 1, 2, 3, and so on. Similarly, -1, -2, -3, and so on. So again, if I'm substituting n is equals to 0, the signal value will be 1, right? So -3 raised to the power 1 will be -3, right? So this is your a. Represent instead of here. So -3, right? So this is your a. If I'm taking a square, so it will be 9 if a is equals to -3. So it is greater than 1. So this is a square. A cube, again it would be negative, right? And so on. In magnitude, this value will be greater, okay, as compared to a square, but it is negative, okay. Again, for -1, so again it will be negative value, right? So it is a inverse. For -2, it is positive value, but again it is less than 1, a to the power -2, right? So it will be -3, again it is a negative value, so a to the power -3, and so on, okay. So likewise, this exponential signal is represented. In previous case, the signal was decaying, it was decreasing, right? In this case, it is increasing, okay. In both cases, the samples have negative or positive values. So here also the sample can have positive, right, or negative values, right? So this is what an exponential sequence is. So in today's session, what we have seen some elementary discrete time signal, starting with unit sample signal, which is also called as unit impulse signal, denoted as del of n. Functionally, it is del of n is equals to 1 for n is equals to 0 and 0 otherwise. Second one is the unit step signal. So that unit step signal is denoted as u of n, and its value is u of n is equals to 1 for n greater than or equals to 0 and 0 otherwise. Right? And third one is the unit ramp signal, which is denoted as ur of n, which is equals to ur of n is equals to small n for n greater than or equals to 0 and 0 otherwise. And last one was the exponential signal, okay. So an exponential signal, as well as unit ramp signal, unit step signal, and unit impulse signal, these are some basic discrete time signal which can be used to perform some complex operations in digital signal processing. These complex operations are convolution, correlation, Z transform, Fourier transform, right? So all these operations will be looking in subsequent lectures. So for now, you have to keep these four signal in mind. We will be also looking the Scilab implementation or demonstration of these four elementary discrete time signal, how these four elementary discrete time signal can be plotted using Scilab code, right? So that we will be looking in our lab session. So in next session, we will be discussing discrete time systems, and we try to identify the output of the given discrete time system. Okay, so that will be discussed in the next session. So thank you for joining today's session.